Hi, welcome everyone to this session on data synthesis for meta-analysis. This is the second part of this session. And in this session, we're going to be talking about synthesizing data when your estimates or your effect measures are continuous. So we all know what continuous data elements are. So for instance, if you want to look at the effect of daily AC and betas on systolic blood pressure that's measured in millimeters of mercury compared to placebo. So your outcome measure is systolic blood pressure, that is a continuous measure. Or if you want to look at the effect of daily glyphosate on random blood sugar compared to insulin, so your outcome is random blood sugar level, and that is measured in millimoles per liter, which is a continuous measure. Or say, for instance, you want to look at the effect of egg intake on infant height for age in z-scores. So you're looking at z-scores, which are continuous measures. When you have this type of measures, it's just, like slightly different from what we've talked about earlier. And typically you want to look at the mean difference because now you're comparing two arms, right? Placebo, the effect of placebo or ACE inhibitors on blood pressure, the effect of glyphosate or insulin on blood sugar, or, like the effect of egg intake on infant weight for height z-scores. So basically you want to take the mean difference, and you're looking at also thinking about the 95% confidence interval or standard error from the individual studies. That's what you extract from the individual studies. One way to generate a pooled estimate for continuous outcomes is by calculating the weighted mean difference. Very similar to what we talked about earlier. Here, the weights are assigned using the standard deviation. Studies with small standard deviation are given larger weights because then they're typically assumed to be more reliable. So when you have the binary outcomes, you're using the standard errors and the effect estimate. For the continuous outcomes, you're using the mean difference. So the difference in the mean, the mean in the intervention group compared to the mean in the control group. And then you are just taking that one estimate, that one effect estimate for your meta-analysis. Now, like I said, the standard deviation, which is a measure of variation around the mean, is what we use to assign the weight. So what happens when your standard deviation is actually high because the outcomes is variable in real life? For instance, if we want to look at the weight of kids in high school, for instance, that is variable. That's a wide range. And so if the standard deviation of the effect estimate is wide, is it because the study is not reliable? Is it because the effect estimate is not reliable? Or is it because it's just in nature? That is how that occurs. When you have a situation where you're not sure if the standard deviation is a measure of reliability, another approach that you can use is the standardized mean difference. It really comes in handy when your standard deviation does not represent the reliability of the studies per se. And sometimes another reason that you want to use a standardized mean difference is when your outcomes are measured using different scales. So the same outcome, but different scales. How do you then, decide what if, for instance, if depression is measured using the PHQ-9 scale and the CESD scale, these are both validated scales for measuring the same construct. How do you then combine them? How do you then combine the scores in a meta-analysis? You can use a standardized mean difference. And what you do is that first you convert all the mean differences into the standardized mean difference by dividing them by the standard deviation. However, the standardized mean difference is unitless. So when you're then interpreting the standardized mean difference, you're interpreting them in units of standard deviation. It is no longer millimoles per liter. It is no longer millimeters of mercury. It is now in units of standard deviation, and we will see examples as we go. So here is an example of the effect of frequent versus infrequent supervised physical activity sessions on mean weight loss at 12 months. So let's take the systematic way of reviewing this, the forest plot. On the left side, you have the study IDs. So these are the studies. These are the study IDs. So the author, and then you have the two categories of interventions. The interventions, the participants that received more contacts, and the participants that received fewer contacts. And you can see the mean difference in the weight. The mean of the weight is, for the group that received more contacts, they lost about 4.8, I'm assuming it's kilograms. And then for the group that received fewer contacts, they lost 5.1. And you can see that. So for more contact, this is the mean weight loss. And then this is the standard deviation. And you can see the same. Coming here, you can see the mean difference. The mean difference is basically the mean in the fewer contacts group minus the mean in the more contacts group. And then you also have the 95% confidence interval. Here, coming to the right side is you can see the line of no effect, basically, at 0. So if the mean difference is 0, it means that there was no effect. There was no difference between the weight loss, the average weight loss amongst people who received fewer contacts compared to people who received more contact. And you can see the boxes. So you can see the boxes or the squares that represent the point estimate of the mean difference, the point estimate of the mean difference. So for instance, this one is, the mean difference here is 0.3. It's positive. So it's on the right side of the 0. And you can see here 0.3. You can see the 95% confidence interval represented by this horizontal line around the squares. You can see the size of this square. So for instance, this study by Saito et al. Has the biggest square. So you know that it has the highest weight in this meta-analysis. And you can see here the weight assigned to this study is 34.1%. And you can see this other study by Tate et al. It has one of the smallest, if not the smallest square. So you will know that it has a relatively small weight compared to the others. And this black diamond, that is your overall, that's your pool's estimate. And you can see the center, negative 2.4 is the effect estimate. And you can see the width or the wings of the diamond, that's the 95% confidence interval around the pooled estimate. And here you can see, it might not be very obvious in the picture, but if you look at the numbers, it crosses the line of no effect a little. So basically, it appears that the mean difference is a difference in the mean weight loss between the two groups, but it's not statistically significant, right? So here you can see the other statistics that you will learn about in later sessions. So the heterogeneity, you can see the test for the overall effect. The z-score is 1.27, the p of 0.21. And that's not surprising because you can see that, you know, the wing of the diamond or the tip of the diamond kind of crosses the line of no effect. So basically, this is very similar to all the forest plots that we saw in the earlier slide, in the earlier session, except that because weight is a continuous measure, the effect estimate is a continuous measure, we're using here the mean difference. And this forest plot really does show it very well, that we're basically just subtracting the mean weight loss among the group with fewer contacts from the mean weight loss among the group with more contacts. So this is an example of how you would use the mean difference. I will now go on and share the next forest plot. So here we are. This is another one that talks about the mean difference in weight loss after 6 months of low-carb diet versus low-fat diet. And you can see here, starting from the left side, the study IDs. So 1, 2, 3, 4, 5. There are 5 primary studies here. Here, it doesn't quite show you the scores among people who got low-carb diet versus people who got low-fat diet. It doesn't show it the way the last slide shows it, but it just shows you the weighted mean difference in kilograms. And you can see for the Brem et al. 2003 is negative 4 kilograms. So amongst those who received low carb diet, and you can see for each of these studies, you can see the mean difference between the group that received low carb diet compared to the group that received the low fat diet. Here in the middle, it's not a solid line this time, it's a dotted line, but you can see here in the middle at 0, the mean difference of 0, meaning like no effect. Is this a line of no effect? So if the weighted mean difference between the two groups is 0, then it just means that there's no difference between the groups, and so no effect. So you can see the line of no effect, and then you can see that the x-axis scale, it just shows you, like the mean difference, the weighted mean difference, the range across all the studies. And then looking at this, these are all big boxes, right? They're almost similar, like they're almost similar in size, the size of the boxes, suggesting that the studies are weighted, like almost equivalently. And if you look at this column, the column of percentage weight, you can see that, from 18.2%, Foster et al. Has a weight of 18.2%, and then Sama et al. Has a weight of 21.5%. So really very similar. So it suggests that their standard deviations are very similar. Here is the pooled estimate, and you can see it here, the diamond. The point estimate is around a little lower than 3, so here it says negative 3.3, and then you can see the 95% confidence interval of the pooled estimate, negative 5.3 to negative 1.4. And here you can see it favors a low carb diet. So it suggests to us, this result suggests to us that people who received low carb diet lost more weight than people who received low fat diet. So basically that's what this forest plot is telling us, and you can see that they use the mean difference. Now we're going to talk about similarly mean difference here in hospital length of stay after esophagectomy at high volume hospitals versus low volume hospitals. And I'm just going to take us through the way to systematically read the forest plot. So the study IDs, you can see all the different studies. The line of no effect, remember, line of no effect, because we're comparing the mean between two groups. If there's no effect, then the mean difference is 0. So the line of no effect is at 0. The x-axis scale just shows you the range of the mean differences and the 95% confidence interval among the primary studies and the overall. Then if you look at the boxes, if you look at the squares, for instance, that represent the weight, this Jafari 2013 study is huge compared to the others. And if you look at this column, you can see that it has a weight of 72.6. So basically almost a third of the weight in this meta-analysis is from one study. And then and you can see also there's almost no horizontal line around it. The standard deviation, the standard deviation is really very small. It's really precise. And then you can see, for instance, look at this study, DIMIC JB, the standard deviation, it's very wide, 95% confidence interval from -19 to 3.07. So it has a small weight. And then look at the diamond, for instance, the pooled estimate. You can see here the pooled estimate, the mean difference in length of stay is -2.98, and it has a very small 95% confidence interval also, -3.7 to -2.79. And so this is your, this is another this is another forest plot. Sometimes you are not just interested in, sometimes you're not looking at data that compares two groups, but you're looking at difference between baseline and follow-up in the same group. So for instance, you want to see the change in the mean difference in weight between kids, the mean difference in a weight of a group of children before they started exercise and after they've been exercising for 6 months, same group of children. So you are now looking at change. You're not looking at difference between two groups. In this case, you can still use the mean difference. It doesn't matter whether it is two different groups or two measurements at different times in the same group. You can use mean difference in this situation. When you think about continuous data, most of the time, most of our statistical analyses are based on an assumption that the data is normally distributed or approximately normally distributed. What happens when your data is skewed? What do? You basically log transform the primary study estimates by taking a natural log of the values. And it's really, I mean, thank goodness for statistical software. You don't have to hand calculate all of that. It's just, like do your log transformation in your R or in your SAS or whatever. And then you log transform each primary study estimate. And once you do that, you go ahead and put it in and run the meta-analysis as usual. And then you present your result as the log ratio of the means. And then when you're talking about it or when you're writing about it, you talk about the difference as percentage difference, not mean difference. And here is an example of daily vitamin D supplementation to shorten the duration of respiratory symptoms. And here you can see, if you look at the x-axis label, it's log ratio of the means. Once you see this, we already know that the data in the estimates in the primary studies were skewed. And so we're going to read it similarly the way we will read any other forest plot. These are the study IDs. These are the authors and the year. And then your line of no effect is still the log ratio, is still 0. So even though it's log ratio of the means, your line of no effect is at 0. You're looking at the boxes. The squares represent the point estimates, and the horizontal lines around the squares represent the 95% confidence interval. You can see here that Goodall et al. Has the biggest square. So it already tells us that it has the highest weight in this meta-analysis. And then here it tells you this is a diamond that represents the pooled estimate, and you can see it is the random effects model. And so here's the diamond. The pooled estimate is very close to 0. It's just reduced, but on the left side of 0 is reduced duration, and on the right side of 0 is increased duration of the respiratory symptoms. Your log ratio of means here is -0.06. And the 95% confidence interval is -0.09 to -0.02. But remember, because it's log ratio of means, you're interpreting as percentage. So you're basically saying there's a 6% reduction in the duration of respiratory symptoms in people who take daily vitamin D supplementation compared to people who did not. So it's kind of straightforward. If your data is skewed, you're taking the log ratio of the means, you're running your meta-analysis the same way. You're taking the natural log of the individual study estimates, then you're doing the log ratio of the means and presenting that in your forest plot, and then you're interpreting the change as percentages when you're writing or reporting your meta-analysis. So that is the end of the class for meta-analysis or for data analysis for continuous variables. I will just ask you to take 10, 20 seconds to think about what your takeaways are from this class. So in this class, we've talked about how you would conduct meta-analysis or data synthesis for continuous variables. And we've said that you would use the mean difference or the standardized mean difference. And we've said that whether you're comparing the change in the mean between two groups or at two different intervals, say baseline and follow-up, for one group, it's okay to use the mean difference. And that you would use the standardized mean difference if your constructs were measured using different scales, or if standard deviation does not represent the reliability of the studies per se. Because remember that even with this, even here, we're still using the weighted average, and the weight that is assigned to each of the primary studies is determined by their standard deviation. So smaller standard deviation, bigger weight, because it is assumed to be more reliable. But in situations where big standard deviation does not mean less reliable study in real life, based on what you know about the data or what you know about that phenomenon, you want to use the standardized mean difference. We also talked about data synthesis and analysis for skewed data. And we said that if your data is skewed, you just take a log estimate of each of the study estimates, and then you do the log means ratio, and then you present your forest plot in the same way that you would normally, and then you interpret the difference as a percentage change. So thank you very much for being with us in this class. See you in the next class.